All right, what's going on? I'm going to go over this problem um, on Leetcode called reverse linked list 2. Okay, let's ignore my code for now, and we can do that later. So, in this problem, it's a it's a it's a problem that's slightly more challenging than the problem of just reversing a linked list. And this problem is asking you to reverse a linked list for a range of the linked list, over a range of the linked list, from some left to some right position. So it's kind of like making a range reversal, you could say, making just one in the reverse list, and it's that's basically how the problem is kind of said. So it's like slightly more difficult than just reversing a linked list. Um, and what else is what else would I say before I get into the problem solving of it? It's uh yeah, okay. I think that's all I would say about it really. It's just kind of like a range reversal. I mean, I was trying to think if there's another way to say it. Like you could say a segment, you could say interval, whatever. Um, but anyways, okay, so you gave this example. 1 points to 2, points to 3, points to 4, points to 5. You want to reverse the range from basically this 2 to this 4, because the left is 2 and right is 4. And this is the result. So now 4 point to 3 and 3 point to 2, and then 5 here. This shows like an example where you kind of deal with an edge case, which we'll have to deal with. So now what I'm gonna do is go over to here, and I'm gonna keep this over in another slide. I'm gonna go over explain like how I would think about this problem. So the first thing is I want to think about like a high level approach and not really think about implementation. So the first thing that you can think is start with a linked list, right? You can just draw a linked list. Say I have a linked list, da 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 da, whatever. Let's say I put my linked list in a box like this. Now my linked list is like I can represent my linked list with just a segment. Seems kind of silly, is this better? I mean, it just allows us to do this at a more abstract level. We just say, oh, some segment here. Um, and then you can just say, that's the wrong one. Now I'll just get rid of this one. But yeah, it's a linked list. And we're just going to say, within this linked list, what we want to do is we're going to be given some left position and some right position. And we want to reverse all the nodes in that range. So, we want to reverse all these nodes. And I'm just drawing like reversing is like, oh, I could say pointing backwards, right? Or I could just say, right now I'm just really generalizing this and just saying the direction of the linked list up to this point is like this, but over here it's going to be like this, and then over here it's going to continue back in this directionality. Now, when you reverse this linked list, um, you want to like then reconnect it. So connect over here and then connect this one over like here, right? So it's a little more than this. You could also view it like this. You say, I have a linked list that goes like this. I have a linked list that goes like this. And you can break it down into these segments, right? So I just broke it down into 3 segments of the linked list. That is, I have the the start segment of the linked list, which just points in the normal direction. And then I have the second segment, which is represented by red and it's pointing in the opposite direction because you reversed all those nodes. So that's the reverse segment. And then you have the end segment, which is also going in the same direction. No, the connections are not reversed. And so if you think about it from this perspective, you could also say, okay, well, um, basically just the middle segment is always going to be the segment that's reversed, right? We could argue that here. Um, so, but when you do this reversal, you actually want to connect these. So the actual like end result is more like this and then you flip this red one. So now I'm pointing in the same direction, but like reality is, um, I'm saying I reverse all the nodes. That is basically if I had node 1 to 2, but let's say, okay, you reverse the connection. So you put the connections like this. But originally the connections were the other way, but now you reverse them. So to see these arrows are pointing in the same direction as this red one here. And then what you're going to do over here is you're going to like flip that and you're going to put the 4 here and the 4 connect to 3, connect to 2, connect to the 1. So it's still your reverse node, but you just kind of like reversed it and you want to reconnect it back to these segments. Okay, so let's use that idea. We want to reconnect these back to these segments and just say, and just make this simple breakdown. You have one segment, you have this segment. You can say this is like, oh, this is like your start segment. And you could say this is like your end segment or something. And then you have your middle segment, which is going to be the reverse segment, or the reverse. So what you can do here is, given this, we can just think about, and at this point in time, we're just saying there's some algorithm to reverse the nodes. We're kind of ignoring that for now. We're taking that as granted because we're familiar with another problem called reverse linked list, so we know there's an algorithm to reverse the nodes. So okay, we're taking that as for granted at this point in how we're thinking about the problem. So if we have this start segment, this reverse segment, and this end segment, well, what you can do is you can see that we're making these reconnections here. So I'm making these reconnections. So what I'm going to do is I'm going to say, okay, if I have my original ones like this, I say, okay, I have one here, I have one here, and then I have this one where I reverse the reverse segment. Let's just draw some of the end nodes. So I'm going to draw, there's a node at the beginning and there's a node at the end. There's a node here, there's a node here. There's nodes in between these, but for illustrative purposes at this point, let's say ignore them, and then we have nodes here. So what we want to do is we want to create some connections here. That is, up here you can kind of see I want to connect this to the 4, but the 4 is actually over here. So you could say you want to connect this node to this node. And then you want to connect this node to this node, like what you're doing here, right? You're connecting the 1 to here. So you can see, oh, I'm connecting this to this, and I'm connecting this to this. And you can see if you do this and you unravel this, rotate this red one 180 degrees, you get back at the picture up here, and you could think of it like that, right? Those are basically like, I think it's called isomorphic or something, but in like graph theory or something, like it has to do with the connections. Like it's the same graph, it's just visually represented differently. Um, but like yeah, so basically this here is going to be this segment, and then you have this segment here. Okay, so given this, you reconnect these, and now at this point you've reversed your linked list and you've reconnected them, and now you've reconstructed the entire linked list. Okay, so at this point this seems really good. So let's start giving these some names. Let's call this pointer, because this is going to be a very important one. Let's call it S, representing like it's in the start segment. And then let's call this one E, representing as in the end segment. And then let's call this pointer, well, it's originally our left pointer, so we'll just call it the left pointer, and we'll call this one the right pointer. That is, this 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 pointer corresponded to the left position originally, and this corresponds to the right position. Of course, once you reverse this, right? Once you reverse this, your left, well, now you're connecting the left to E, and you're connecting S to R. So you're kind of like reversing it, right? Which makes sense because that's the whole point of the problem, right? If you have your left one and you have R node and you reverse this whole linked list, well, now you should have your L here. Oh, sorry, you should have R here and you should have L here, which is what you do. And then you connect S to the R, and you connect L to the E node. And when you make those two connections, you reconnect the entire linked list. Okay, so we kind of have an algorithm here. We kind of know we need to keep track of 4 pointers, And we know we need to have a method to be able to reverse this linked list, and we need to have a method to be able to do some of these other things. But let's just think about some obvious edge cases that could come up before we kind of get into it. So an obvious edge case is, let's say you have one node, and your left and right position are guaranteed to be, they're going to be at the same location. So your left and right node are going to be at the same position. Well, your S is going to be in the same position. Um, Actually, yeah, before we go into this one, let's go into, because actually this one's very important. Because what do you do with E in this situation, right? Where does E go? So I'm saying S goes here, and I'm saying LR goes here. Well, okay, this is actually already problematic right here, before we even talk about E. This is problematic because you want to connect S to R. Okay, so this is creating an edge case where, like, okay, you can't do anything, right? You have one node, your L is pointing it to it, your R is pointing to it, your S pointing it. So what you can do is, for every single linked list, you can create this like head node or some like pseudo head node, or I think they call it dummy nodes a lot of times, or sentinel node. So you can create this dummy node, like I guess it's called dummy because it's like a dummy variable, like it's just put there to um, eliminate this edge case to allow the algorithm to be more elegant and simple. So if you do that and you create this, and now it's going to be connected to your node. So now you'll never have one node because you're always adding this dummy node. So the smallest linked list you could have is now containing two nodes. And in this case, the S can just point to the dummy node. In this case, if L and R are pointing to this one node, which they will be because they are heavily pointing node, then the dummy node would just be S. Is it a problem that L and R point to the same node? Well, actually, let's get into that after we talk about what's going to happen with E. And let's ignore L for right now. Let's just look at this connection, right? We have to be able to make this connection for this approach up here to work. And so if we create this dummy node over here, we can still create this connection even if there's just going to be one node. Because now we can connect that dummy node to the R. And at the end of this algorithm, and you could even visualize like this, you could say, if I have some linked list, some arbitrary linked list in here, right? I'm always creating a dummy node out here. And at the end of your results, all you have to do is return everything basically that's after the dummy node. So you just ignore it in the return results. Um, and so that's kind of what it's like. It's kind of like just saying, you have a linked list, you attach some nodes at the beginning. Um, and S will start there and everything, and it will help out for if like in this case I said it was one node, but it would also help out if for some reason L is at the first node, because now your dummy node can have S, and now if R is somewhere over here, you can still make the connection to R. You reverse these, and then you can reconnect S to R. You can still make the connections, but at the end result, what you're going to return is going to start from this node, because the dummy node you don't return. Okay, so but this one node is very illustrative of edge cases. So okay, you have that. So we're going to add this dummy node. It makes sense that it's going to simplify our logic, because now if we add it, we can still apply the same logic we're agreeing to up here, which is we're going to always connect the S to R. Because now we add a dummy node, we're guaranteeing that there's always an S. We can always connect it to R. Let's say for E though, so when you have just one node and we add the dummy node. Actually, let's do it over here. Let's do it in this picture. We add this dummy node. This is what it kind of looks like for one node, a one node linked list. And let's say you have L here. So L has to be pointing to this node, because L and R have to be positions, correct positions within the linked list, and this is the only position that's available. So they have to be the same. But now what you have to do is you're going to make this connection L to E, right? So this is also an interesting case, because it's kind of like maybe you could say a trivial case or something, because it's a range of just one node. So like up here, I represent the range, and usually you think, oh, it's going to have like multiple nodes, you're going to reverse them. But like it could be the trivial case where the left and right are the same, and it's just one node you want to reverse. And how do you reverse one node? You don't reverse one node, right? But this logic would still apply with one node. Like you kind of have to prove that. I mean, we could prove that right now. We could prove that this logic applies to even if it's just one node. Um, kind of right here, right? Because if you're doing L, if you have L and R, and you connect S to E, now you have to do this logic. You have to connect L to E. Well, connecting L to E can be done like this, but you don't have another node, so E can't be at another node. Well, that's fine. What you could do is E is going to be at a null, so that's reasonable. If E points to null, you can still make the connection L to E, and you're still allowed to make the connection S to R, and you return this as your result, but returning this as your result is still just one node, right? Because it's kind of implied in linked lists. Linked lists always end with a null. That is, no matter what linked list I give you, the last node here, you don't draw it, but like it's actually connected to a null. Like it has a null connection. And that's why it's the end of the linked list. It's the last node in this linked list. But it's always connected to null no matter what. Your last node is always connected to null. So given that, it doesn't seem too silly to apply a null here and to just say, sometimes it's going to be pushed off to null if we just don't have an element. So like really this will apply anytime whenever R is the last node and the next node is null. Then you're always going to put E over here. And so on. So those are the edge cases for this problem, and I think that's what makes this problem a little more difficult. Um, so the next step is how do you implement these? So we basically just want to follow the strategy of this. Let's write down the strategy that what the algorithm will be. The algorithm will be we need S, L, R, and E pointers to nodes, and we need to like move them to the correct location. So they need to be the in their position that they need to be in, right? Based on what we said up here, like S needs to be here, it needs to be right before L, and E needs to be right after R, and then you're going to reverse. And that's another step in the algorithm is you need to reverse a linked list. You can just imagine that linked list that you're actually reversing though is from L to R. You're reversing this linked list. So you need to reverse a linked list. Um, and then at the end, the last step of the algorithm is just make the S to, what was it, S to L, S to R, I mean, yeah, S to R, and L to E connections. So like reconnect everything, and then that's it. That's the whole algorithm. So okay, so we can go into, so now I'm just going to go over the implementation of this algorithm and how you can do it. So yeah, let's do that next. So okay, so how can you do this? You can take first step um, is you create a dummy node. Actually, I think the best way to do this is can I? No, I don't know if I can do this. But the best way to do this is to think about what the code will do. So at the beginning, you're going to have a dummy node, right? You're going to add that. So, let's give ourselves a linked list. It's easiest to maybe do this by having a linked list example and just simulating how the algorithm can work. Let's just set our left to 4 and set our right to 7. Okay. And then you can always imagine that this points to null, right? Okay. In this case, this is our segment that we're going to reverse, and we're going to create the end results. Okay, so the first step of the algorithm is it creates a dummy node and points it here. So that's my dummy node representation. Okay, step 1. I guess I forgot to write that in this algorithm steps, but yeah, you have to create the dummy node. Uh, you do that, and then you are going to set, so you want E to point to here, but what you can do is you can use E as like a pointer that moves through the whole linked list until it gets to that point. And you can use it for the reversal segment. So let's put E here at the beginning. And then what you're going to do is you're going to iterate through left times. So because our goal is to get S to be here, right? We're going to try to get S here and L here. But um, we want to do it in a certain way, right? For instance, let's go over a way that we can't do it. Let's say E is here, and you say, okay, I'm going to move E along. Move E along. I move E to here. Then I say, okay, set S to point to here. I mean, you could do it that way. Sure. Um, yeah, you could do it that way. Actually, I don't think I implemented it that way, but that might actually be better. You could just do that. You could just say E is here. Or actually, I guess you don't need E at this point. You could just have S. Right. Okay. Yeah, so you could just have S, and then you're just gonna move S, or well, S starts at the dummy node actually, so it starts here, and so you're gonna move it 1 time, 2 times, 3 times. You want it to be here, so you're gonna move it 3 times when left is 4. So that's kind of like you could say you're moving it left -1 times. Okay, and now you get S to here. So S is in the correct position that it needs to be in. Now S is there. What we're going to do next is what is left. Well, we know where left is. Left is right here. We can get that really easily by just doing s dot next, saying L is equal to that. Okay, and then what we're going to do is, and this step might seem a bit counterintuitive, but we're going to set right to be null. And the reason for that is going to become clearer because we're going to use it in the reversal algorithm. Because if we use a reversal algorithm, we can get it to like its correct position and also use it for reversing the array. So, okay, there's one other step you want to do though. You want to disconnect S from L. So you want to disconnect it for a bit. So when you disconnect it, that means it's going to be pointing to null. We're going to assume that nulls are at the end of. We're just not going to write them. Okay, so right now S is just like pointing to nothing. We disconnect it. And now we're going to begin the reversal algorithm. So in the reversal algorithm, the first step is well, actually we're gonna have an E variable. The E variable is going to be like our variable uh, to just kind of like keep track of where we're at as we go along, because basically we're just going to use E because we want to get it to this point. So yeah, we're gonna start with E here. The first thing you want to do is you want to point this E node to R. So you're pointing this to null, um, which seems counterintuitive this n, but it's really just saying you're going to make this our end node in a segment. So then what you do is you're going to set the right node equal to E. So right node will go here for now, and then you're going to move E along. I'm just going to do it like this. So you move E along. You're going to hold on. So yeah, when you connected this node back here, you erased the connection here. So you're basically just saying when you connect by connecting to null, you're removing the connection it had over here. And now you're getting to the next step where you moved E, and now you're going to move this connection back here. You're going to reverse that one. And okay, well after you're done with that, you're good to go. You can move R to E now, and then you can move E again here. You're going to do the same thing. You're going to reverse the connection to the R node, right? So you're basically just saying E dot next equals R here. and then you're gonna move E again and move R again. And then this is your last node, so you're gonna do this same thing one more time, and you're gonna reconnect this to here, and then you can move E one more time and move R one more time. And I don't know if I represent these here. So we've kind of R started here and it kind of moved throughout. Okay. So R is no longer in these locations. Let's clean it up real quick. And now E has made its way to the end. Not to the end, but to the location where you want it to be for the next step when you're going to connect L to E. Okay. So originally you connect this one to null, and that was the reason why you really did that is because it was connected to this node. So by connecting to null, you're really just saying it's a terminal node. So let's just remove this null connection, and let's just say this is what the linked list kind of looks like. So now what we want to do is we want to make the connection S to R. So if we do that, we're going to make this connection S to R, and now you can see that these all go in the same direction. And then we need to make our last connection from L to E, and that's it. Now you've reversed this segment, and you've constructed a whole new linked list with that segment reverse. So I'm going to rewrite my code a little bit with this information. Because here actually I set E equal to dummy, but now I realize I can set S equal to dummy. I can maybe simplify this, and it's just going to be, and then just do this left minus 1 times, and then just keep moving S forward. And then by doing this, then your left node will be s.next. Your right node you set to none initially, and then you want to disconnect the S node. But before you disconnect it, no, this is fine. And then you're also going to set E equals to left node. Okay, and then you're going to begin the traversal because you're going to do this because the left node is going to be fixed. It's going to stay. Now the two nodes that are going to move are going to be right node and E, and they're going to move in that pattern to reverse all the connections here. And they're going to move the length plus 1 times as we did. So this code stays the same. So next point is e.next. You kind of have to save this because you want to point e.next to right node, but you still want to go to the actual like next node of E. So, and then you point the right node to E. So you're just moving the right node along, and then you're moving E along the linked list. And then this is the reverse connection, right? Pointing it back, reconnecting E basically. Because E was connecting to the next node, but now you're saying connect to the previous node. Your previous node is your right node, though, in this case, just because like we're agreeing to using those pointers. I mean, once you're done with that, all you have to do is reconnect s.next to the right node and reconnect the left node to E, and then you want to skip the dummy node here. Oh, then you have the dummy. Let's check that this works because this is I just changed a little bit of the code. I guess I realized I could have made it simpler here. Okay, yeah, so that's this explanation of this problem, an explanation of an algorithm. And that's it for this one. Thank you for watching.